My name is Christy Green, and I'm from the Sustainable Thermal Systems Laboratory at the Georgia Institute of Technology. Today, I'm going to be presenting non-intrusive load monitoring of water heaters using graph signal processing. In this study, we wanted to disaggregate low-resolution data from advanced metering infrastructure smart meters to determine the energy consumption of electric air source heat pump water heaters. The AMI meter in this case is assumed to have a sampling frequency of 15 minutes. And residential AMI meters, like the ones we considered in this study, account for approximately 88% of the total number of AMI meters deployed in the United States today. Our interest in heat pump water heaters began with previous work conducted at STSL on the optimization of a residential microgrid. The neighborhood shown here is the Alabama Power Smart Neighborhood at Reynolds Landing, located in Hoover, Alabama. Reynolds Landing is a neighborhood of 62 homes containing a variety of IoT appliances, and the houses are all connected to a local PV array. Each house within the neighborhood has a hybrid electric air source heat pump water heater, and our previous work included the modeling and optimization of the water heater and the HVAC loads in the houses. Disaggregating the power signals of these controllable appliances from the electrical main signal would allow for the estimation of demand response potential at the neighborhood or even the regional level without the installation of intrusive monitoring equipment. To perform non-intrusive disaggregation, graph signal processing was selected due to its ability to perform with high accuracy using low-resolution sampling rates over short training periods. In graph signal processing, the structure of the signal is embedded into a graph to show spatial and temporal correlations among the samples. The algorithm demonstrated here was developed by researchers at the University of Strathclyde. They performed benchmarking of this algorithm using the RED and refit datasets against state-of-the-art algorithms, including hidden Markov model and decision tree approaches, and they determined that the graph signal processing algorithm had higher accuracy for most appliances disaggregated. The graph signal processing algorithm is not new, but the application of the algorithm to the disaggregation of heat pump water heaters is new. In graph signal processing, we represent the signal using a graph defined by a set of nodes and a weighted adjacency matrix. In this case, the set of nodes is a set of power values, and the adjacency matrix is calculated using the change in power from one time step to the next in the Gaussian kernel weighting function. A graph signal S is determined by evaluating the change in power at each time interval. If the change in power is greater than the threshold value T naught, the value for S is 1. If the change in power is less than the threshold value, S is equal to -1. After defining the graph, we need to find an approximate solution for this optimization problem. We're approximating the solution as the minimization of the smoothness term, which has the closed form solution shown here for S star. S star is the total graph classifier. The values of S star are compared to a threshold value. If S star exceeds that value at any point, the appliance is considered to be operating, and the appliance's mean power is substituted for S star in the signal. The resulting appliance signal is then subtracted from the main signal, and the process is repeated. The data used in this study were gathered at the Oak Ridge National Laboratory Yarnell Station Test Facility. Devices present in the house include a heat pump water heater, electric resistance water heater, HVAC system with a continuously variable compressor and fan, a pool pump, an electric vehicle charger, 2 humidifiers, and 2 heaters that simulate the presence of 2 occupants, and several unknown loads that include lighting, computing equipment, and miscellaneous plug loads. The heat pump water heater and the HVAC system installed at Yarnell Station during this test period were the same models that were installed in the Reynolds Landing smart neighborhood that we saw in an earlier slide. The hybrid heat pump water heater was disaggregated in 2 operational modes. First, it was disaggregated when it was operating only as a heat pump, then in a hybrid mode with both the heat pump and the electric resistive elements operating either simultaneously or independently. Some characteristics of the power traces of the loads present in the house are provided in these 2 tables. Here, IDU corresponds to the indoor unit of the HVAC system, and ODU corresponds to the outdoor unit. We can see that the mean and the variance of the heat pump water heater vary significantly between the 2 cases, and that the HVAC outdoor unit is introducing a significant amount of variance into the main signal. To prepare the data, first, data from all 1-minute time intervals at which non-numeric values occurred were removed. These instances amounted to less than 1% of the original dataset. The dataset was then downsampled from 1-minute intervals to 15-minute intervals by taking the mean at each interval. We know that there are several things that may influence the accuracy of the algorithm. If the magnitude of power change with respect to the main signal is too low, a signal may become mixed with similar signals. If the number of appliance operational states is high, or the appliance is continuously variable, one appliance can seem like several appliances. If there's a large amount of fluctuation in the base load, a signal that was capable of being disaggregated at one point may later be hidden within this base load. If the appliance is operating infrequently, this can lead to a rough graph, which is more difficult to disaggregate. And of course, the order of the sequence in which the appliances are disaggregated will also affect the outcome. So in this case, if an inaccurate appliance signal is removed from the main signal early on, the error will propagate through all subsequent disaggregations. Our primary interest was to determine the potential accuracy of the supervised disaggregation of the heat pump water heater in the presence of a variety of different loads. To do this, we disaggregated the heat pump water heater signal from several different constructed main signals while the water heater was operating in both the heat pump and the hybrid heat pump mode. After we observed the accuracy of disaggregation in the presence of all these different loads, we looked at some metrics that might help to determine the potential for disaggregation for a given appliance, as well as help us to select the optimal order of appliances in the disaggregation sequence. One metric we used for this purpose was the coefficient of determination, or R squared. So in this case, the R squared value was calculated to determine how well the change in power of an individual appliance signal, in this case the water heater, is represented in the electric main signal. Main signals were constructed using the combinations of loads listed here, as well as the whole house main signal. The signals were constructed during the period of time where the heat pump water heater operated only as a heat pump, as well as the period in which it was operating in the hybrid mode. The accuracy of the NILM algorithm is reported here as the F measure. The R-squared statistic, as mentioned previously, is the coefficient of determination calculated between the change in power draw of the appliance signal and the main signal. So it's a predictive metric in this case and not a measure of the NILM accuracy. We see that when the change in the appliance power is more closely correlated with the change in the mains power, as shown by R-squared, the disaggregation, as measured by the F-score, is more accurate. In this case, higher accuracy also correlates with the percentage of total power attributed to the water heater in a given period. Results demonstrate that the ordering of appliance disaggregation will be important, and that the appliances with high variance, like the HVAC outdoor unit, must be disaggregated or removed from the main signal prior to disaggregating the water heater. Knowing the correlation between F-measure and other metrics like variance or R-squared, we may use these metrics to choose the disaggregation sequence with which we can achieve the greatest accuracy. In addition, because we're interested in a specific appliance, in this case the water heater, we may check the chosen metric for the appliance initially to determine whether or not it may be disaggregated first. If it can't be disaggregated first, we can check this metric again against the new main signal in each subsequent pass of the algorithm until it's capable of being disaggregated. This would reduce unnecessary appliance disaggregation and in turn improve computational speed. So in conclusion, we determined that the electric hybrid heat pump water heater may be effectively disaggregated in the presence of other loads as long as they have low variance. So it's very important that you properly sequence the disaggregation order. And we also determined that in a supervised or semi-supervised algorithm where something about the appliance signal is known prior to the disaggregation period, predictive metrics like R-squared or variance can be used to sort the appliance disaggregation order to both improve the accuracy of the algorithm as well as reduce the computational speed. So thank you for attending my talk today, and now we have time for questions.